In this question, we are prompted to use the theorem of Pythagoras. This can be found on page 16 of our formula book. It states that in a right-angled triangle with a hypotenuse of C and lengths of A and B for the other two sides, we'll have C squared equal to A squared plus B squared. Here, the word hypotenuse refers to the side which is opposite the right angle. We need to find the length of the line R to Q. Let's mark this unknown with X in our diagram. Now, let's focus on the right-angled triangle RPQ and apply Pythagoras' theorem. In our formula, C represents the hypotenuse, the side which is opposite the right angle. Here, that's the 6.5. The other two sides of our triangle should be labelled with A and B. Here, I'll label the X as our A and the 3.3 as our B. Now, let's sub into our formula. 6.5 squared is 42.25 and 3.3 squared is 10.89. To find the value of x, we'll need to rearrange our equation into the form x is equal to something. Our x appears on the right-hand side, and to isolate it, we'll need to get rid of the square and the plus 10.89. The opposite of addition is subtraction. So to get rid of a plus 10.89, we should subtract 10.89 from both sides. Performing the calculation on the left gives us 31.36 is equal to x squared. Since the opposite of a square is a square root, the next step will be to square root both sides. Performing the calculation on the left-hand side gives us our final answer. X is equal to 5.6. Since all the other lengths in the triangle are measured in meters, that's the unit we'll want to use here. The angle alpha appears in a right-angled triangle, RPQ. The SOHCAHTOA result is very useful in this situation. This can be found on page 16 of the formula book, and it says that if we're given an angle A in a right-angled triangle with hypotenuse H opposite O and adjacent A, then sine of A is equal to O over H, cos of A is equal to A over H, and tan of A is equal to O over A. To use this result, we must label our triangle appropriately. The angle we are concerned with is alpha, so let's label that with A. The hypotenuse H is the side opposite the right angle. In our triangle, that corresponds to the 6.5 meters. The opposite O is the side opposite our angle of interest. Here, that's the 3.3 meters. The adjacent A is the third side which is remaining. Here, A is equal to 5.6 meters. Each of our three trigonometric ratios, sine, cos, and tan, involve 2 out of the 3 sides of the triangle. Since we actually know all 3 sides of the triangle, we have some flexibility here. Sine, cos, and tan are all options that will work. I'm going to pick sine and use the fact that sine of A is equal to O over H. We have alpha in the place of A, O equal to 3.3, and H equal to 6.5. So let's sub these in. We're trying to find alpha, and this appears on the left-hand side of our equation. However, it appears inside a sign. We'll need to get rid of this to find alpha. Whenever we want to remove something from an equation, we need to perform the inverse to both sides. Our calculator has a built-in function, sine inverse, which is defined to be the inverse of a sine. So we should take sine inverse of both sides. On the left, the sine inverse and the sine cancel. Now, performing the calculation on the right-hand side gives us an answer of 30.5102. We are asked to present our answer correct to the nearest degree, so rounding this off, we get alpha is equal to 31 degrees. The key to solving this question is the fact that angles on a straight line always add up to 180 degrees. If we focus on the line from P to S, we'll notice that the angles on this line are 31 degrees and beta. Since angles on a straight line always must add to 180, we get the equation that 31 plus beta is equal to 180. To find beta, all we have to do is subtract 31 from both sides. This gives us the answer that beta is equal to 149. In this question, we are prompted to use the cosine rule. This can be found on page 16 of the formula book, and it states the following. Given the three sides, A, B, C, and the angle A squared is equal to B squared plus C squared minus 2BC times the cosine of A. It's worth emphasising here that the side which is labelled with lowercase a must be opposite the angle which has been labelled with uppercase A. Due to symmetry, the other two sides can be labelled B and C in any way we want. So, we're asked to find the length of the line from R to S. Let's label this unknown with X. This side appears in the triangle RQS. Let's focus on this when applying our cosine rule. The cosine rule only involves one angle, capital A. We only know one angle in our triangle, 149 degrees. So let's label this with capital A. The side opposite this angle must be labelled with lowercase a. So here we'll label the X with a lowercase a. We can label the other two sides with B and C in any way we like. Here I'll label B as the side which is 8 meters long and C as the side which is 5.6 meters long. Now that we've identified the values for all our letters, let's go ahead and sub into the statement of the cosine rule. From here we can simplify. 8 squared is 64, 5.6 squared is 31.36, and, using our calculator, minus 2 times 8 times 5.6 times cosine of 149 comes out as plus 76.8022. Adding up the numbers on the right hand side gives us x squared is equal to 172.1622. To find the value of x, we'll need to get rid of this square. The inverse of a square is a square root, so here we should square root both sides of our equation. When we perform the calculation on the right hand side, we get x is equal to 13.1211. Since we were asked to give our answer correct to the nearest metre, we round this off to get a final answer of x is equal to 13 metres. In this question, we need to find the length of an arc. There's a result on page 9 of the formula book which will help here. It says that the length of the arc, L, from an angle theta in a circle with radius r is L is equal to 2 pi r times theta over 360 degrees. We want the length of the arc from T to S. To be able to use our formula, we need to know the size of the angle which spans this arc. Let's label it with x. Finding this isn't too difficult. We have a fact that the angles on a straight line always add up to 180 degrees. If we look above the line from R to T, the angles that are on it are 149 and x. Since angles on a straight line must add to 180, we have x plus 149 equal to 180. To find x, we should subtract 149 from both sides. This gives us that x is equal to 31 degrees. An alternative approach to finding this angle would be to use the fact that opposite angles are always equal. In our formula, theta refers to the angle spanning the arc. Here, we'll have theta equal to 31 degrees. R is equal to the radius, and in our diagram, this is equal to 8 meters. Let's sub these values into our formula. Performing the calculation on the right hand side gives us L is equal to 4.3284. We're asked to give our answers in meters correct to one decimal place. So rounding this off gives us our final answer of 4.3 meters. We must find the area of the sector SQT. Looking to page 9 of the formula book, there's a helpful result here. It says that the area of the sector A from an angle theta in a circle with radius r is A is equal to pi r squared times theta over 360 degrees. In this formula, theta refers to the angle which spans the sector. In our diagram, we'll have theta equal to 31 degrees. R is the radius, and in our sector, we have a radius of 8 meters. To find the area of our sector, all we have to do is sub in these values to our formula. When we do the calculation on the right, we'll get out 17.3137. We're asked to give our answer in square meters correct to one decimal place, so rounding this off gives us our final answer of 17.3 meters squared.